Any questions over the homework?
Yes, sir.
Yes.
3.9, number 11.
Okay, so we're gonna have to talk about logarithmic differentiation. We did talk about briefly how to find the derivative of functions like this. So we have this is the function that we were talking about last class. It's of the form, one function of x raised to another function of x's power. So if that's our, this is our y. What method that we can use here is based on the relationship between e and natural log. So we can say that this is equal to e to the g of x times the natural log of the base, h of x. And then that way we just have that complicated looking function expressed as e to a power. So we can look at that, the function that we're given f of x, and say that f of x is equal to e to the ln of 8x times the natural log of sine x. And it's a little more complicated this way because when we say the derivative of e to a functional power, it's e to that very same power times the derivative of the power, which involves a product rule and a chain rule. So we're going to wait on this until after we see the process of logarithmic differentiation. The logarithmic differentiation makes this easier, sort of a relative term, but it makes this easier. So we'll hold off on that because I think logarithmic differentiation for functions of like h to the g is easier than writing it as e. Okay. So we might revisit this problem as well as an additional example. But we're going to have to hold off on that for now. Any other questions on the homework? So in 3.9 we did leave off talking about or bringing up the notion of logarithmic differentiation. And so the name is kind of indicative of the process. But why would we want another method for taking a derivative? So we could say we could use that last function from our homework as an example. Consider whatever it was. Sine to the natural log. Or, something even more dreadful looking, like x cubed minus 2x squared plus 1 times the square root of 3x minus 1 all over x squared plus 4 to the 8th times, I don't know, the sine of 5x. So
So what's after the plus in that polynomial?
Oh, just one.
Okay.
We're not gonna actually work that one. It's just an example for motivation as to why we want another method. So functions like the one we just saw involve a product rule and a chain rule. Functions like the second y we've written down involves a quotient rule, multiple product rules, and multiple chain rules. So you've got, to take the derivative of this function here with normal rules is really tedious. And so logarithmic differentiation, the process is highly dependent upon the properties of logarithms, which hopefully you have a chance to look at. Because there's only 3 properties of logarithms that we utilize. There's one for powers, there's one for products, and there's one for quotients. So, we'll just say here, in order to find y prime, and just so we're clear on which y we're talking about, I'm just going to call this function h of x. So in order to find y prime, we must use quotient, product, and chain rules. So that's a lot of work, but properties of logarithms. Properties of logarithms allow us to rewrite a few things. Powers as multiplication, two, multiplication as sums, and quotients as differences. So you take a little more complicated operations, if you will, powers, multiplication, and quotients, and you turn them into much simpler operations with properties of logarithms. So that's why we use this method sometimes.
Wait, is that a u or is it an o? Like the second one?
Where?
Sums? Like the multiplication as, is that after the as, is it an o or an
Oh, it's a u.
Okay, cool.
Okay, so the logarithmic differentiation, the process. Logarithmic differentiation procedure. It's pretty much what its name implies, except for there's a implicit step there. So in order to perform logarithmic differentiation on any given function, you first take the logarithm of both sides. You can use any logarithm you want because all logarithms have these 3 properties we mentioned. But the natural logarithm's derivative is cleaner, right? Because when we take the derivative of the natural log, we just have 1 over x. But if we take the derivative of, any other logarithm that we like, even the log base 10, what's the derivative of the log base 10?
over x natural log term?
Yeah, 1 over x natural log of the base. So the other logarithms, with the exception of the natural logarithm, have that extra constant factor in the denominator. So in this process of logarithmic differentiation, it's always easier to introduce the natural log instead of some other logarithm. So we're going to take the logarithm of both sides, and then the process is to differentiate. But the sort of the implicit step here is once we've taken the logarithm of both sides, before we take the derivative, we're going to simplify our function using properties of logarithms. Simplify the function, whatever is given, using properties of logarithms. So we'll write the steps down and look at examples. So we take the log of both sides, simplify using properties of logarithms, and differentiate both sides, or take the derivative of both sides. Differentiate both sides. And then solve for y prime. However you denoted your derivative, we've got to solve for that. So we'll just look at an example where normally we probably wouldn't think to use logarithmic differentiation, just to show that it is consistent. And then we'll look at other more complicated expressions. So here's an example. We'll just start off with something really basic. So if we have y equals to x cubed, we know the derivative here, just keeping in mind, is 3x squared. So in a lot of instances where you don't have tons of operations happening, it's easier just to do a regular derivative with the rules we already know. But we could do logarithmic differentiation on this. And the first step is to take the natural log of both sides. So we take the natural log of both sides. The ln of y, there's nothing we can simplify there. The ln of x cubed, we can simplify that using properties of logarithms. So log both sides, then we're going to simplify this using properties of logarithms. This has to stay as is. What can we do with the natural log of x cubed?
Bring 3.
Yeah, 3 can come out front to multiply just the natural log of x. And then that's as far as we can simplify using properties of logarithms. So we take the log, simplify with properties of logarithms, then we take the derivative. It's super important that you simplify as much as you can with properties of logarithms. Otherwise, you're really not doing yourself any favor. If you just simplify a really complex expression using properties of logarithms, and you just apply one rule to that, you're still going to have this complicated expression that now involves logarithms. We end up with logarithms regardless, but if you don't simplify fully with properties of logarithms, it's almost like a waste of time to even do logarithmic differentiation. Okay, so what's the derivative of the natural log of y? derivative of, okay, so the derivative of 3 ln of x, we can do
Y prime
that.
over Y.
3 over x, or 3 times the derivative of the natural log of x, is 3 times 1 over x. Okay. So I thought I heard someone say, what's the derivative of the natural log of y?
Y prime over Y.
Y prime over y, right? Y is really a function of x. So this is an implicit differentiation step on the left-hand side. So we say the derivative of the logarithm is 1 over the argument times the derivative of the argument. So it's 1 over y, y prime, or y prime over y. So that's implicit differentiation with y, ln of y. And then we need to solve now for y prime, which means we're just going to multiply through both sides by y. So we have y prime is equal to y times 3 over x. But what is y?
X cubed.
X cubed. Y is really x cubed. So we have y prime equals to x cubed times 3 over x, which gives us our derivative, 3x squared. So again, in an instance like that, you wouldn't use logarithmic differentiation. It's just a power rule. You could, is what we've shown is that you could totally do logarithmic differentiation if it works. But we're sort of reserving this process for more complex looking functions that have multiple operations involved. So the y prime over the y is always present when you do logarithmic differentiation. Every time you take the derivative of the natural log of y, which in this process you always will, you will always have y prime over y. Solving for y always entails us multiplying through by y, and then substituting our original function back in for y. So we don't do that here. We wouldn't say, well, isn't that just the natural log of x cubed? We don't do that here. You just leave your y so that you get y prime over y, then you solve. Once you solve for y prime, then you plug back in your y. So does anyone have any questions on that? Of the log of both sides? Simplify with properties of logarithms, take the derivative, solve for y prime, and then you resubstitute y. Okay. So then we're going to look at a couple more complicated ones. Or I guess a little more involved. So use logarithmic differentiation to find y prime. Example 1, we'll start off with y equals x plus 1 squared divided by x minus 2. Again, maybe not necessarily a function you would use logarithmic differentiation on because it's just a quotient rule. Basically a chain rule to take the derivative of the numerator. But we're going to use this process here. So we're taking the natural log of both sides of our equation. And simplify then in terms of our properties of logarithms. In ln of y just has to be left as it is. Nothing we can simplify there. But on the right hand side we have the log of a quotient. So the log of a quotient turns into what?
difference.
Difference, yeah, so what does the difference look like? What will we have?
Natural log of x plus 1 squared minus natural log of x minus 2.
Okay. Natural log of the numerator minus the natural log of the denominator. All right. The second term here, natural log of our denominator, x minus 2, we can't do anything with that further to simplify it. We can simplify the first term on the right-hand side once more, because we've got the log of something raised to a power. The power can come out front and multiply the logarithm. So one more property of logarithms here to simplify this as far as we can with properties of logarithms. So keep this notation consistent. If, a lot of people immediately will want to take the derivative of the left-hand side just because they know what it is. But we're still talking about the natural log of y is this function here. So if you write y prime over y is equal to all of this, then you're going to totally mess up the derivative. We haven't done any differentiation yet. Is everybody clear on that? We've just simplified in terms of logarithms. So completely simplified now in terms of logarithms. At that point, then we take the derivative of both sides. So implicit differentiation, y prime over y, is equal to the derivative of our right-hand side. So we have, what's the derivative of 2 natural log of x plus 1? So 2 is a constant, it's out of the derivative. Derivative of the natural log of x plus 1 would be
1 over x plus 1.
1 over x plus 1, right? Derivative of the natural log of anything is 1 over the argument times the derivative of the argument. The derivative of x plus 1 is what? 1. Minus, what's the derivative of the natural log of x minus 2? 1 over x minus 2. Okay, so since it's just 2 times this, I'm going to write this up here. So we got this. So maybe we'll just put a note here. From here, we're differentiate, take the derivative, both sides, with respect to x. Again, this works because y is a function of x. What function of x is it? The function we started off with, the x plus 1 squared over x minus 2. Okay, are there any questions on where we're at? Got to solve now for y prime. Which means we're going to multiply through by y and replace y with what it was originally. So we have y prime is y times all of this stuff. In other words, y prime is x plus 1 squared over x minus 2 times this quantity, 2 over x plus 1 minus 1 over x minus 2. So that's our answer. If we take the derivative of our original function using the quotient rule, you would have a slightly different representation of the derivative. But if we simplify this derivative that we have here, it should be identical to the derivative using the quotient rule. So like these types of problems on the exam, I don't expect you to multiply all of this out. Just leave it as y times whatever you had on the other side. Okay, questions on this? So let's look at, well, let's look at a few more like regular sort of algebraic functions, and then we'll look at some like that example from my homework, question number 11. So let's do a similar one that we wrote down earlier, x cubed minus 2x squared plus 1 times the square root of 3x minus 1, and have all of that over x squared plus 4 to the 8th. So on the exam, it'll say explicitly, use logarithmic differentiation to find the derivative. If it doesn't say, you can use any method you want. But on the exam, one question will explicitly say, use logarithmic differentiation. So at least once on the exam, you'll have to do this. So again, something like that is a really good candidate for logarithmic differentiation because we have products, we have chain rules, we have a quotient. So we take the log of both sides, natural log of both sides. And then we're going to simplify. Using the properties of logarithms. So again, if this is all you did, you haven't helped yourself at all, right? Because now you got to take the derivative of the log of this function. You might as well just take the derivative of your original function. But once again, on the left, the right-hand side, you have the log of a quotient. You have to look at like the overall structure of the function. Yeah, it has products and powers, but it is something divided by something else. So we applied the quotient property first and say that it's the log of the numerator. Log of the numerator minus the log of the denominator. And we're just keeping track that this is still just the natural log of y. Is everybody okay with that? Okay. Again, don't just stop here, because then you have to take the derivative of this product, the log of this product, which involves a product rule and a chain rule. So we're simplifying even further with properties of logarithms. What can we do with our first term on the right?
Add it.
We can add them, so what would that look like?
Natural log of x cubed minus 2x squared plus 1 plus the natural log of square root of 3x minus 1.
Okay, good. So it's just the natural log of factor 1 plus the natural log of factor number 2. We get 3 factors plus the natural log of the third factor, etc., etc. Minus, what can we do with the natural log of x squared plus 4 to the 8th?
Bring the 8 to the front.
Bring out the 8 to the front. So we have 8, wait, we'll do this. We'll have 8 times the natural log of our x squared plus 4. So we're done with that one. Once you have the log of a sum of things or difference of things, you can't do anything with that. Same thing with the log of our cubic thing here. It's the log of something plus something else. There's nothing we can do with that. So unfortunately, we do have to leave that alone. We've left the last term alone. Is there anything we can do with the natural log of the square root of x minus 1? 3x minus 1?
Multiply by 1/2.
By 1/2, right? Remember the square root is the same thing as the 1/2 power. So I'm just going to rewrite that here just to save some space. But the square root is the 1/2 power. 1/2. Again, this is still natural log of y. We haven't taken any derivatives at this point. So the only other step we can perform is moving the square root, the power, out front to multiply that other logarithm. So we have the natural log of x cubed minus 2x squared plus 1 plus 1/2 natural log of 3x minus 1 minus 8 natural log x squared plus 4. I mean, you still have some complexities in the function, right? But you don't have product, quotient, and chain rules left anymore. At most, you have the derivative of the natural log with a chain rule. So from this point, we've simplified completely in terms of properties of logarithms. Now we're going to differentiate both sides with respect to x. We have y prime over y is equal to, what's the derivative of the natural log of x cubed minus 2x squared plus 1? What's the derivative of this thing here?
3x squared minus 2x over x cubed minus 2x squared plus 1.
Okay, yeah, 3. So what did you say? You said 3x squared minus
2x over the original.
Okay, right, but it's minus 4x, right?
Oh, 4, yeah. Bring the
Yeah.
4 with the 2.
So remember, the derivative of the log of anything is 1 over the thing. So we have 1 over this thing times the derivative of that thing. What's the derivative of x cubed minus 2x squared plus 1? It's 3x squared minus 4x. Then we have our plus 1/2 times the derivative of the natural log of 3x minus 1. What would that be?
Wouldn't that be 3 over 3x minus 1?
3 over 3x minus 1. What do y'all think? One over the argument 3x minus 1 times the derivative of 3x minus 1, which is 3. So you got 3 over 3x minus 1. Just like it is over here, right? It's just derivative. The derivative of the logarithm of anything is the derivative of the function inside divided by the function inside. Minus 8 times the derivative of the natural log of x squared plus 4, what would that be? Yeah, 2x over x squared plus 4. One over the argument times the derivative of the argument, which is 2x. So hopefully you can kind of get that in your head, like it's almost automatic, because it makes this taking derivatives of functions like this so much easier. So yeah, it looks kind of sloppy because we've got something kind of gnarly plus something else, and then we've got to multiply all of that by the original function. But it's a lot more efficient to do this than product rule, quotient rule, chain rule, et cetera, et cetera. And then we'll solve for y prime. So we're going to multiply all of this stuff by the original function. Which was x cubed minus 2x squared plus 1 times the square root of 3x minus 1. And all of that was over x squared plus 4 to the 8th. So that's why, and we got to multiply by all of this stuff. We could clean this, a couple of these up a little bit, but that's the basic idea. You could say it's 6x minus 2 on the bottom, or just leave the 2 out. It doesn't really matter. And then we have our minus 8 times the 2x, so we have a minus 16 x over x squared plus 4. So all of that is our derivative. We could possibly simplify it, but again, you shouldn't worry about that on the exam. That's super tedious to have to simplify. So especially problems like that, simplify as much as you can with properties of logarithms. Otherwise, you're just making the derivatives that much more difficult to compute. Are there any questions on that example? Okay. So let's look at x to the x. Let's look at these kinds of functions. We'll start off with this one. It's the most basic f of x to the g of x type of function we can look at. And with the process of logarithmic differentiation, again, we should know that we can rewrite these types of functions in terms of e and natural log, which once we get to chapter 4, later in chapter 4, we're going to have to rewrite these kinds of functions as e to the x ln x. So the property that we're using is that something like that is the same thing as e to the b times the natural log of the original base. So we should know that even though we can use logarithmic differentiation now on something like this, you should know that, especially when we get into chapter 4, we have to utilize that fact. So one, we can rewrite using e and ln. So we're gonna do that. Y, rewritten is really e to the x times natural log of x. So I guess the advantage of doing this is that we know how to take the derivative of e to whatever power. The derivative of e to whatever power is e to that power times what? The derivative of the power, right? So the derivative of the power, x times ln of x. So I know like that's just the notation I use, meaning we still have to take the derivative of that. Some people just aren't a fan of that notation. So like if whatever you need to write to indicate to yourself that you have to take the derivative of that, maybe you can just put a prime out here or something. It's not a technical notation, so you might get in trouble, later on in math. But if you don't like this notation, just find something else that works for you to indicate, hey, I still have to take the derivative of that thing. Okay, so derivative there is a product rule. We have e to the x ln of x times, a product rule is going to give us two different terms, usually. So we have the first times the derivative of ln of x. Derivative of ln of x is that. First times the derivative of the second plus the second times the derivative of the first, which is 1. So we'll write that. And then we can simplify inside because we have x over x, which is 1, plus ln of x times 1. So we just have 1 plus ln x as the derivative of x times natural log of x. So hopefully everyone's okay with that. We've done derivative of e's to powers quite frequently. The only other step that you might see is that since we rewrote the original function, x to the x, so just make a note here, we rewrote x to the x as e to the x ln of x. The only other modification would be maybe at this point, writing that e to the x ln of x as x to the x. And that's our derivative there. So sometimes the issue is with a function like sine x to the natural log of 8x, you still have a product and a quotient rule left over when you rewrite as e to the ln. Here we just had a product rule and it wasn't too bad, but you can still have multiple rules rewriting y in terms of e and natural log. So the other process is, instead of rewriting it, we'll just use logarithmic differentiation. And we're sticking with the function as it was originally expressed, y equals x to the x. So we're going to take the log of both sides. And simplify using properties of logarithms. So what can we simplify? Yeah, we've got the log of x raised to a power. The power can come out front and multiply. So we've got natural log of y equals to x times the natural log of x. Okay, that's as far as we can simplify. Then we take the derivative of both sides. So we've got y prime over y equals the derivative of x ln of x. We already found that. We just used the product rule to find that. We found it to be 1 plus ln of x. And then we multiply through by y to solve for y prime. But remember y was x to the x. So we have x to the x times 1 plus natural log of x. So same derivative that we had using or rewriting it as e to the natural log. So with functions like, x to the x, sine of x to the natural log of x, those types of functions, you always have these two methods that will apply to those.
I don't know that they show up a whole lot in the real world. They are fairly strange looking functions. X to the x, you see all these little discrete points here. It's not continuous on this side, but it's continuous over here. Let's go back home because I don't know, you may be able to see those, maybe not. So why would an x to the x be defined for some of these values? What's a situation where what x value wouldn't work here? For instance, what could we not compute if x were so we see, I don't know if I zoom in they might go away, but we could certainly define -2 to the -2, right? If x is -2, then we have y equals to -2 to the power of -2, right? So that's just 1 over -2 squared, which is 1 over 4. So what wouldn't work as an input for x in this function?
Odd numbers.
Odd numbers? Can we compute -3 to the -3? That's just 1 over -3 to the third power, or 1 over -27.
0?
0? Certainly wouldn't work for 0 because we have 0 to the 0th power. Okay. How about -1/2? Would that work? Could we do that? Yeah, because you got to take the square root of a negative number now, because this is -1/2 to the power of -1/2, which is 1 over our -1/2 to the positive 1/2 power. And now that's the same thing as 1 over the square root of -1/2, which is not a real number. So anything that has any negative number with an even number on the bottom won't work for x. But also, when we think about us saying that x to the x was the same thing as e to the x ln of x, then looking at it as e to the x ln of x sort of gives us a better indication as to what the domain should be if those two things are the same, right? So the domain for e to the x ln of x would be what?
All whole numbers.
Whole numbers? Yeah, certainly whole numbers would work, but even fractional numbers work, right? No, the restriction of e to the power of x natural log of x, the restriction comes from what part? It's not x, right? I can plug in anything for x and still raise e to that power, but the natural log has a restriction, doesn't it? Can I evaluate the natural log at negative numbers? Can I evaluate the natural log at 0? No. The domain is from 0 to infinity. And we sort of see that there, right? There's that weird looking sort of parabolic shape. It starts at 0 and then it goes off to infinity. 0 to infinity. So here are those two functions, exactly the same. So we know the domain of that function from 0 to infinity. We can see on the graph that maybe, at 0 it's 1, but it's actually undefined. So that function has, x to the x has a hole at the location 0, 1. And then that's what we talk about later on in chapter 4, like how do we find stuff like that. So anyhow, you've got two methods to take the derivative of functions like x to the x, sine of x to the natural log of x. One of them you can rewrite using e and natural log. The other method is logarithmic differentiation. Does anyone have any questions on that? So we can go back then to that homework question. So sine of x, and it's that quantity raised to the natural log of 8x. So we already showed if we rewrite it, we still have a product and a chain rule. So let's just go ahead and do logarithmic differentiation on this. We're going to take the log of both sides. And then simplify. So ln of y then is equal to what? Natural log of 8x is our power that comes out front to multiply. So we have natural log 8x times the natural log now of sine x. Can we do anything else? Natural log sine, just have to leave it alone unless you wanted to write it as, well, yeah, there would be no reason to do that. So we're going to leave that alone. We could say the natural log of 8 times x is the natural log of 8 plus the natural log of x, right? For something like these linear type arguments in the logarithms, it shouldn't be like difficult. We said to simplify completely in terms of logarithms, so that's what we'll do. So we'll write ln of 8x as ln of 8 plus ln of x. Let me do this. rewriting that thing as two things. As long as you can see that that derivative's, you know, not difficult, there's no reason to break that up, but just for consistency, we said simplify as much as we can. So since we broke that up into two things, we have to remember that both of these are times the natural log of sine x. Again, that's still natural log of y. We haven't taken derivatives yet. So when we rewrote this on our homework question, we said we could rewrite this as e to that power, which involves a product rule and a chain rule. Not only a chain rule to take the derivative of e to that power, but a chain rule for the natural log of sine x and for 8x as well. So you see the situation we're in with after logarithmic differentiation is not too much different. We just don't have e to that power, right? Like that's the only difference. If we were to look at it as, let's rewrite this function using this procedure, you're pretty much at the exact same step. Because if we exponentiated both sides of our equation at this point, what's e to the ln of y equal to?
E to the y.
Huh?
E to the y. Or, no.
Not quite. Just y, right? E in natural log, e to the natural log of anything is just that thing. So we have just y on the left-hand side equals e to that power. Isn't that what we had when we rewrote that function originally in terms of e in natural log? So it's virtually the same kind of procedure, it's just slightly different because, you know, we're not actually exponentiating both sides. Okay. So either way you go, you still have to take the derivative of this natural log times that natural log. So differentiate both sides, y prime over y is equal to, well, over here on the right we have a product, so we have a product rule that we need to apply on the right-hand side. So we have the first times the derivative of the second. What's the derivative for the natural log of sine?
Might be 1 over sine x.
Times?
Derivative of sine x, which is cosine.
Yes. So let's do that here, kind of to the side. Derivative of the natural log of sine. Or we know that's a chain rule because it's not ln of x times sine of x. It's ln of sine x. So we do 1 over the argument times the derivative of the argument. Cosine over sine. Derivative of natural log of sine is cosine over sine. Or we could just say that's what?
Cotangent.
Yeah. Okay, so there's the first times the derivative of the second. And we do plus the second times the derivative of the first. What's the derivative of our first term? 1 over x, right? ln of 8 is just a number. Derivative of that is 0. Derivative of ln of x is just 1 over x. So derivative of the second is 1 over x. So I mean, it doesn't look that great, but I mean, the function was pretty complicated. Okay, so we have cotangent times these two terms in red, and we have ln of sine x all over x. That's y prime over y. We'll solve for y prime. So I'll rewrite this in a second. It's y times all of this stuff. Remember, ln of 8 plus the ln of x, we could rewrite that as what? If we reverse the properties of logarithms. Yeah, ln of 8x times cotangent plus ln sine of x. So remember, it's the natural log of the sine of x divided by x. So hopefully no one's tempted to cross the x's out. And then we just rewrite y as in terms of x, which was whatever we had, sine x to the power of natural log of 8x. Times all of that stuff. I think my math lab's sort of inconsistent with which ones it wants you to simplify and which ones it doesn't care about. So if you have something like this and you enter that in and it doesn't work, I guess if that's your first attempt, you try to simplify this. If it still doesn't work, then just send me an email. I'm okay looking at those and seeing if you got this answer. That's fine to me. But they may want something different or something more simplified, I should say. But that's our derivative there. Okay. Anyone have any questions? Yeah.
So it would be acceptable in a natural log of 8 plus natural log of x to write that final answer is just the natural log of 8x?
Yeah, that's probably better, just so you have just one thing multiplying the cotangent.
Okay.
Yeah. Because the derivative of the natural, we've seen this a lot, the derivative of the natural log of like a linear function, mx plus b, the derivative of that is always still 1 over, well, the derivative of mx, natural log of mx, is just 1 over x. We should say that. So I think it's probably easier not how we chose to rewrote the natural log of 8x as the natural log of 8 plus the natural log of x. I think it's just easier to leave it as ln of 8x. Any other questions? So we might look at 1 or 2 more examples for functions like this. I'm just sort of curious here. So yeah, you got a weird derivative because look, the function's super weird.
when you look at your derivative, you can tell where the derivative is not defined, right? So this derivative won't be defined. We've definitely got a natural log present. So the natural log of this quantity has to be larger than or equal to 0. X has to be larger than or equal to 0 here. Another ln there. You've got the natural log of sine. So you then have to figure out when is the sine function larger than 0. And then we have the cotangent. What's the derivative, or what's the domain for the cotangent? You've got the intersection of all of those domains together would be the domain of your derivative. So you've got a lot of exclusions. We see that here. Can't define derivatives here, here, and so on, and so on, and so on. All right. Well, we'll take a break and finish 3-dyne after we get back.
I could just return it. I could just return it afterwards. I
mean, if you really want to throw $100 in return it, it's
I'm gonna mess with you with a single value.
So we'll look at one more function like this, and the function we looked at earlier, the x to the x function. If we were going to graph that, we then have to have a means to compute if the domain of this function is from 0 to infinity. We have to know what happens as we get closer and closer to 0. Just like when we talk about the natural log function, we say, well, what does the natural log do as we get closer and closer to 0 from the left-hand side rather? We just know by its graph that it approaches negative infinity, and that sort of came out in the process of like comparing it to its inverse. It's the same idea with this function. Since it has a restricted domain, what happens as we get closer and closer to 0 from the right-hand side? Does it have an asymptote like the natural log? Does it approach something like 1 where it's not defined? Those kinds of things need to be answered. Basically, in how we would determine the end behavior of x to the x is that we have to compute a limit as x approaches 0 from the right. And the problem with computing that limit, for instance, is that we get 0 over 0 to the 0th power. And 0 to the 0th power is something that we can't initially determine. Like, we can't just say 0 to the 0 is 0, 0 to the 0 is not 1. So we do encounter a couple of things where the value of it in the sense of a limit is ambiguous. So you can't really determine the value of 0 to the 0 as a limit. But we would have to be able to determine that value on a function like x to the x to determine what its end behavior was. The function we're going to look at now, it's the 1 plus 1 over x to the power of x. If we wanted to determine that function's end behavior, then we also have a similar issue. So here's the function 1 plus 1 over x to the power of x. And we see just by looking at the graph that it appears to flatten out. It actually flattens out towards infinity to the value of e. I think we mentioned this last time. But the way that shows up is, well, what's the limit at infinity of this kind of function, or this particular function anyways? What we end up with is 1 to the infinity. Remember, in the terms of a limit, it says that the base is approaching 1 and the power is approaching an arbitrarily large number. So things like this don't have a set value. Like, we can't say in the sense of a limit something like 1 to the infinity is equal to 1. Because here's an example where it's not, right? this thing out towards infinity, 1 to the infinity in this instance happens to be e. So then we've got to talk about or look at methods that'll help us compute limits like this, which is super closely related to what we're doing. Not in the sense of taking a derivative of the function, but the process that we're applying to take these derivatives is very closely related to the process of how we find limits like that. So we'll see that later on in chapter 4, but anyways, I think it's worth mentioning that, you know, those types of functions we do revisit. So again, you've got two options. Since it's like a function of x to another function of x, we could rewrite it in terms of e and ln, or we could just take the natural log of both sides and use logarithmic differentiation. So here again, you just have the log on the right side, you have the log of something raised to a power. And when we simplify with properties of logarithms, we'll just move the power out front, multiply the log 1 plus 1 over x. So you still have a product rule involved in the derivative and a chain rule involved with the natural log argument. But at least with these things, you're able to make some sense out of this now, because those types of functions are neither power functions nor are they exponential functions. So, you know, going back to this function here, if you take the derivative like it's a power, and you say it's x to the power of x minus 1 times x, then that's totally wrong, because that is not the derivative of that function. You know, of course, if it were like x to some power like that, then yeah, the power rule is applicable there. But the power rule isn't applicable to something like this. And sort of indirectly, we're seeing what kind of rule is actually involved with taking that function's derivative. We've got a product rule and a chain rule, but it involves these logarithms as well. Okay, so that's as far as you can go with properties of logarithms. So we're going to take the derivative of both sides. And then maybe over here, we'll take the derivative of the left-hand side, or the right-hand side rather, derivative of x times natural log 1 plus 1 over x. So that involves a product rule where we have the first times the derivative of the second plus the second times the derivative of the first. And the derivative of the first is 1, so we just have the second here. All right. Then we've got to compute the derivative of the natural log of 1 plus 1 over x. So what's the derivative for natural log 1 plus 1 over x? It's not just x. So we do 1 over 1 over the argument times the derivative of the argument. What's the derivative of 1 plus 1 over x? What's the derivative of 1?
0.
Plus the derivative of 1 over x? You got two choices, right? You could use a quotient rule for the derivative of 1 over x, or you could rewrite 1 over x as x to the negative 1. So negative 1 times x to the negative 2. Is that derivative there? Negative 1 times x to the negative 2, or negative 1 over x squared? So again, what we have in green right there, that product is just the derivative of the natural log of 1 plus 1 over x. Then we have this thing here, plus this thing here. Any questions on what we've done? And we can simplify this because we have x squared times the quantity on the bottom there in green. We have our negative 1 times x on top. And then we have our x squared times this quantity here. So we can get rid of that complex fraction if we multiply through by that x squared. So we have x squared times 1 plus x squared times 1 over x, or x squared divided by x. Everybody okay with that? And then we still have that other natural log hanging out here. And then we can simplify our negative x over x squared plus x a little bit more. We can factor out an x on the bottom and then divide that with the x on top. We have negative 1 over x plus 1 plus that other natural log. So that was kind of a pain. You would have been dealing with a very, very similar derivative, though, had you rewritten it as e to the x ln of 1 plus 1 over x. You still have to take that derivative, so where do you go? All right, so that's the derivative of our right-hand side, x times the natural log of x. Any questions on that? And then we have our y prime is equal to y times all of that stuff. So we have y was 1 plus 1 over x to the x times this stuff here. That's the derivative of y prime.
So that, again, that function there, y prime, tells us how do you find the slope of this purple function here? What's the slope at 5? I put 5 into my derivative for x. I have that slope. Any questions on this at all?
So we'll end the 3.9 there then if there aren't any questions. Is the last section in chapter 3 where we actually get a new derivative rules. We're looking at the derivative for the inverse trig functions. We still have 3.6 and 3.11 left from chapter 3. So before we look at, we're probably just going to look at one. The formula for the derivatives is on the next page. We'll look at one and how it comes about. But I think it's worth remembering the domain and range for the inverse trig function, so we'll just put that here. For inverse sine and for inverse cosine, their domains are the same. The domain for both of those functions are -1 including to +1 including. So closed interval from -1 to 1. The range for inverse sine conventionally is from -π/2 to π/2. And for inverse cosine, the range is from 0 to pi. Both of those closed intervals. So that, you might have talked about it in trig or in pre-calc, how or why that is, but it's based on the idea that for a function to have an inverse, like there's the sine function. For instance, for any function to have an inverse, it has to be a 1-to-1 function, meaning that it has to pass a horizontal line test. So wherever, like here, clearly sine doesn't pass a horizontal line test. So sine, cosine, they're not 1-to-1 functions, meaning if we found their inverse just based on their entire function, it wouldn't be a function, right? Because the inverse would sort of look something like this. If we graph the inverse, it would sort of look like, like that. It's not a function. So before you found the inverse sine, you said, well, how about we restrict the domain of sine so that it is 1-to-1? We said, all right, well, go from here to here. Let's just talk about sine from here to here. Then sine at that point becomes a 1-to-1 function. So I can talk about the inverse sine function if I restrict the domain of sine from -π/2 to π/2, right? So sine's domain is restricted from -π/2 to π/2. The domain becomes the range of the inverse. So that domain becomes the range of the inverse. This was the original restricted domain of cosine, right there. Oops. But that's the original restricted domain of cosine to make it a one-to-one function. And of course, sine and cosine both sine outputs values from -1 to +1. The range of sine now becomes the domain of inverse sine. So that's kind of where all of these things came from. I don't know that you necessarily need to remember that for anything we do, but I think it's a really important concept. Anyhow, there's inverse sine and cosine. We have inverse tangent and inverse cotangent. Both of those functions have a domain of all real numbers, because the range of the range of cotangent and tangent functions, they're like those elongated S shapes. Cotangent and tangent output all real numbers, so their inverse's domain is all real numbers. The range for inverse tangent is -π/2, the open interval from -π/2 to π/2. And for inverse cotangent, the range is 0 to pi, the open interval from 0 to pi. Now this, it doesn't matter. I mean, it does matter that we know these. Hopefully you know these. But when we see like a derivative formula, so the derivative of these inverse trig functions are defined for specific values. Okay, secant and cosecant, inverse secant and inverse cosecant. They both have a domain absolute value of x has to be larger than or equal to 1. So x has to be larger than or equal to 1 or less than or equal to -1. Remember the graph of like secant or cosecant looked like this, where this value here was 1 and this value was -1. So you didn't have anything output there. So you don't have anything input into the inverse functions. Okay, domain for both of those. And then the output of inverse secant, just think about that as 1 over cosine. Whereas cosine 0 π/2. So we would say that the inverse secant's range is from 0 to π/2, and then from π/2 to pi. So it's kind of like tied to the range for inverse cosine, except for at π/2 and at the endpoints. We just had to split it up at π/2 basically. And you got a similar thing here with the inverse cosecant. Like if we think about the original function of 1 over cosecant, or sorry, 1 over sine rather as cosecant, and say, well, sine's not defined at 0, at pi, etc. So then we can like look at this range and say, well, 0 is in this range. The inverse cosecant can't output 0. So it's from -π/2 to 0, and then 0 to π/2. Somewhat related to the inverse sine, because cosecant and sine are related.
I was going to ask, because I know sometimes in my math lab, you don't necessarily have to put the unison sign in there, you can just replace that with a comma.
Mhm.
Were you prefer a unison sign on the test, or could we just put a comma in there instead?
I mean, the union's more technical, because it's like this interval or that interval.
Okay.
My math lab would usually say like, separate your answers with commas or something like that. So yeah, I'm not going to test you directly on these things. We should remember them. The reason I'm bringing them up is because when we justify the derivatives of all of these inverse trig functions, both their domain and their range have to come into the equation at some point for us to determine what their derivatives are. So it's very similar to that derivative of our 6 trig functions, where we said, well, if you know the 3 on the left, which were sine, cosine, and tangent, then you knew the other 3 derivatives. These are even easier. If you know the derivatives of inverse sine, inverse tangent, and inverse secant, then the derivatives of their inverse cofunctions are just the opposites. So the derivative of inverse sine, 1 over square root of 1 minus x squared. The derivative of inverse cosine is just the negative of that. And they all fit that pattern. So really you get like a 6 for 3 kind of thing here. Derivative of our trig functions are also trig functions because trig functions are periodic. They all repeat. The derivatives of our inverse trig functions, notice that they're not periodic, they're just these algebraic functions. Because the inverse trig functions don't repeat. They all had restrictions on them. Like we had to restrict sine like this. It's not a periodic function anymore. We wouldn't expect its derivative to be periodic or repeat as well. So we're going to look at the derivative for the inverse sine and work through that to see where it comes from. As far as the exam goes on these inverse trig functions, it's just going to be a matching. So I'll say, like one column is all of these functions, the other column is all of the derivatives, and you just have to match the inverse trig function to its derivative. I will say though that 2 extremely important ones that you see quite often through Calc 1 and Calc 2 are the inverse tangent and the inverse sine. So those are really common when we start looking at antiderivatives, which continues through Calc 2 and Calc 3. But as far as the material, I'm not going to actually have you compute derivatives of inverse trig functions on the exam. You just need to be able to match the inverse trig function with its derivative. Okay. So proving these derivatives are what they are involve, the easiest way involves implicit differentiation. So we're starting off with this function and we want to know what y prime is. So we're going to remind ourselves that if we're talking about the function y equals to the inverse sine of x, we say x is a member of the interval from -1 to 1, and y is a member of the range of the inverse sine, which was inclusive -pi/2 to pi/2. So we're gonna keep that in mind. This is where x is. Specifically, this is where y is. That's the more important one, and we'll see why in a minute. Okay, and so we don't know the derivative of inverse sine. Let's say we don't know the derivative of that, but I can rewrite this equation. I can say y is the inverse sine of x. That equation is equivalent to the equation what? How could I rewrite that in terms of something I already know the derivative of?
Y is 1%.
So, yeah, no, don't get these confused with the reciprocal functions. Sometimes, just for clarity, sometimes the inverse trig functions are written as arc, like ARC in front of them, just so we know that that's the inverse sine, because this isn't the same thing as 1 over sine. positive 1. So don't get those confused.
Or rather, could you say x equals sine of y?
Yeah, right. If y is the inverse sine of x, we just take the sine of both sides. Right, so the sine of y has to equal to the sine of sine inverse. They're inverses of each other, so they cancel out. So if y is inverse sine of x, that means the sine of y is x. And then we have implicit differentiation, because we know how to take the derivative of sine, and we know how to take the derivative implicitly. So implicit differentiation, we have, what's the derivative of the sine of y implicitly? So like if I told you, what if I told you to take the derivative of, find the derivative of the sine of any function of x? What would you say the derivative of that is? Of f of x times the derivative of f of x, right? Times the derivative of f of x. Remember, f of x is y. So what's the derivative of sine y? Right, cosine y times y prime. Derivative of x is 1. So, looking at the formula for the derivative of inverse sine, it's 1 over the square root of 1 minus x squared. It doesn't look great at this point because we have things in terms of y, and we've got a trig function in there. So that's kind of where the fact that for the inverse sine, y has to be in this interval. That's what it comes in to help us figure out what exactly we're looking at when we say y prime is 1 over cosine y. Because we don't want this in terms of y, we want the derivative of inverse sine of x in terms of x. Okay. So there's the derivative. We now need to figure out what cosine y is in terms of x, basically. So we need cosine y. In terms of x. So at this point, it doesn't seem all that hopeful, because what we have in terms of x is the sine of y. So instead of cosine y, if we had like some representation of sine y instead, then we could relate it back to x, because we have sine y related to x, not cosine y related to x. So we're going to use the Pythagorean identity. Sine squared of something plus cosine squared of something else, or the same thing rather, is always equal to 1. Which means that we have a representation for cosine squared in terms of sine squared. Which is more what we want, right? We want to represent cosine y in terms of x. We don't have cosine y in terms of x, we have sine in terms of x. So the first thing we need to do is represent cosine in terms of sine, and then we can represent sine in terms of x. So cosine of y is the positive and the negative square root of 1 minus sine squared y. And what do we know sine squared is? Sine squared of y is or sine of y quantity squared is
1 minus cosine squared.
x squared. It's x squared. Sine of y is x, so sine squared is x squared. Okay. let's write that. Cosine of y is plus or minus the square root of 1 minus x squared. So that's great. We've got cosine in terms of x, but we don't want two different derivatives if we can avoid that. We don't want to say our derivative is 1 over the positive root of 1 minus x squared, and our derivative is 1 over the negative root of 1 minus x squared. So this is where, at this point, we've got cosine of y in terms of x, but at this point, this is where we go back to our original y, right, from y equals inverse sine of x. We know if we're dealing with that function, y has to be in this interval. And so does that tell us anything about cosine? So cosine y in the, cosine of y when y is in the interval from negative pi over 2 to pi over 2. So y is a member of this interval. Is there anything we can say about cosine if y is in this interval? There's cosine of y. Cosine of y, cosine of our input. But we know our input's from negative pi over 2 to positive pi over 2. What do we know about cosine?
It's positive.
It's always positive, right? So here's cosine in that interval. So the cosine of y it's larger than or equal to 0. On the endpoints it's 0. But the main idea is that cosine isn't negative on that interval for y, which means cosine of y isn't the negative square root, it's just the positive square root. So what that means, therefore, our y prime is 1 over the positive square root of 1 minus x squared when y is the inverse sine of x. So it's just what our formula said. You don't need to remember the derivation. I think it just lends itself to a more insightful, more insight as to where these derivatives come from. So if you look at the other ones, they're all very, very similar to that process. They're just involve something a little bit different. The issues come with inverse secant and inverse cosecant. So we see we have the absolute value of x in both of those. So more or less you have two different derivatives for inverse secant and inverse cosecant depending on where x is. So when we derive it the same way with inverse secant and inverse cosecant, you can't get rid of that plus and that minus like we could here. So that plus minus just gets absorbed into an absolute value, which is why those derivatives have absolute value in them. But all of these derivatives follow these columns here. So inverse sine and inverse cosine's derivative is valid for x in between -1 and +1, right? So we said, well, the domain for inverse sine was -1 to +1, where we can include -1 and +1, but the domain of the derivative doesn't include those endpoints. We can see why, because it's 1 over the square root of 1 minus x squared. But also, when you look at the graph, the formula says, okay, well, the
derivative isn't defined for -1 and 1, which are the endpoints for inverse sine. And we can just look at that right quick to see what happens on that graph. So here at the endpoint, or this endpoint, what happens to our derivative or our tangent line?
Becomes undefined.
It's undefined, right? Because we have a vertical tangent line at that point. So there's the graph of inverse sine. We can define a derivative everywhere except for here and here. All right. So the way this works out is that what we're looking at here with these formulas is just the derivative of the outer function when the outer function is one of these trig functions. If you've got any other function like the inverse sine of 2x or the inverse tangent of the natural log of x, then the only addition we have here is the chain rule, where we have to multiply by the derivative of the argument. Again, you're not seeing those, but they are there. This is the derivative for the inverse cosine of x is -1 over the square root of 1 minus x squared times the derivative of the original argument, and all of them are this way. And we're just not seeing that because it's 1 for all of these, just like it was with all of the other functions we looked at. Do y'all have any questions about any of that? Yeah. Yeah, sure.
Where did the, how did you get it to come from?
Oh, that was from the original implicit differentiation. Implicit differentiation, and then we solve for y prime. So that was that 1 over. Yeah, and then cosine we saw was just the positive root of 1 minus. Yeah. Any other questions? All right, we will look at a few of these just because you have homework over this section. But like I said, for the exam, you know that, you can match those up. You're fine for inverse trig functions on the third exam. So we'll have a few examples for these. So let's say y was the inverse sine of 2x. The derivative then says that we have to do 1 over the square root of 1 minus the argument squared times the derivative of the argument. That's just a chain rule applied to the, like we said, the table just gives us, or the theorem, whatever they're calling it, just gives us a means to take the derivative of the outer function inverse sine. Okay. Does that make sense? And then we have the derivative of 2x is 2 over the square root of 1 minus 4x squared. So like, whatever we're taking the inverse sine of, just you will have, that set of parentheses there. We just replace them with whatever argument we we have for the inverse sine. So let's say y were the inverse sine of the natural log of x. Then its derivative would be 1 over the square root of 1 minus the argument squared times the derivative of the argument. So that's the way you can think of the inverse sine of anything. Its derivative will always be this right here. That's always what it is. And this, of course, is the argument of your inverse sine, whatever that happens to be. Okay, so we've got the derivative of the natural log of x is 1 over x, so that's in the bottom with our radical. 1 over x times this radical, 1 minus natural log of x. Quantity squared. So the natural log of x, that whole thing being squared, it's totally different than the natural log of just x squared. So the ln of x squared, that's just the natural log of x times x. But the ln of x squared, sometimes written like the trig function, ln squared x, that's ln x times itself. So there is no property of logarithms that we can use on this thing here. Two totally different things. So we're just going to leave ln x quantity squared as ln squared x, or ln quantity squared. That's our derivative. Okay, does anyone have any questions on that? They're all very similar to what we're doing here. The tricky ones are the inverse secant and inverse cosecant, just because they involve natural logarithm, or the absolute value rather. And usually with the absolute value, you then have to determine, do I have to leave the absolute value, or is there a way I can get rid of the absolute value? So those are usually the only ones where it's a little bit more thoughts involved on how just to simplify them. So let's say we had the function inverse secant of the square root of x. I suppose there's a few ways to go about this, but it really boils down to absolute value around things that could be positive or negative, or that could be negative. You don't need absolute value around things that are positive. So we take the derivative. What's the derivative of the inverse secant? One over
Absolute value square root x squared minus 1.
absolute value square root of that thing squared minus 1 times the derivative of that thing, right? Here, that thing is the square root of x. So 1 over the absolute value of the argument times the square root of the argument squared minus 1 times the derivative of the argument. That's the form the inverse secant's derivative always takes. So here with the absolute value of the square root of x, do we need that? No, is the square root of x, is the square root of a number ever negative? So we don't need the absolute value on that. So let's write that out in the next step. We'll say it's 1 over just the square root of x times the square root of x squared. Well, we can simplify that too. Let's do that. What's the square root of x squared?
X.
X. How do we know it's just x and not absolute value of x? It's under the square root, meaning x has to be what? Positive, right? X is already a positive number by implication that it's the square root of x. So this right here implies that x is larger than or equal to 0 already. Otherwise, you would have a complex function, not a real function, or imaginary. So this is x. The absolute value of the square root of x was just the square root of x because of this right here. So we have square root of x squared minus 1 under the radical times the derivative of the square root of x, which we've seen that enough, 1 over 2 square root x, or 1/2 x to the negative 1/2. And then we can multiply these two roots together, root x times root x, and simplify that. So we have just x times the square root of 1, x minus 1 rather, all over 1, or 1 over all of that stuff. That's our derivative. So this, just be careful, because what we've written here as x larger than or equal to 0, that's not the domain in this case for the inverse secant. That's just the domain for the square root of x, right? The inverse secant function had a domain. So the inverse secant of something, we'll just call it w. The domain is that input w had to be an absolute value larger than or equal to 1. W had to be larger than or equal to 1. What we're inputting here for w then is the square root of x, right? So we would say, well, in order to determine the domain of the inverse secant of the square root of x, I have to determine when is the absolute value of the square root of x larger than or equal to 1. Or when is the square root of x larger than or equal to 1 is what we're finding. So just be mindful of that. This is not the domain of the entire function, just for the square root.
I don't know, maybe my math is off, but what happened to the 2 in the bottom? I know once you know when
Oh, yeah.
apply 2 square roots, it undoes it, but.
Yeah, that 2 should still be there. Thank you. Any other questions on this one? We might look at a couple more examples here in 310, and we've got to do 3.6 and 3.11. But 3.6, 3.11 are application sections. So this is all of the derivative rules that we see. All right. Well, if there aren't any other questions, we're going to end there. There's not enough time to do another one, so we'll see ya.